So I'm going to talk about some aspects of the CFT sort of grammar dual to quantum gravity and matter on BTZ backgrounds. This is work done with my student Anton de la Fuente. So this is the starting point. BTZ is just the ADS-3 version of the eternal black hole. And so here's a picture of here's a picture of the black hole sitting as an object inside of ADS-3 in space-time. And here's the now standard dual with a hot CFT living on the boundary of that space-time, one dimension down, namely 2. Here's the Schwarzschild geometry of the black hole. And the only thing unusual here is I've just changed, just for later convenience, I've changed the angular direction sigma to not be 2 pi periodic, but to have a period which depends on the Schwarzschild radius of the black hole. So in these funny coordinates, the Schwarzschild radius of the black hole looks like it's at 1, but that's just for convenience. And in these funny coordinates, the temperature of the CFT that's dual to this is sort of 1 over 2 pi. Okay. So you can probe this black hole using boundary correlators coming out of the boundary. And that's dual to now thermal correlators of local operators in the CFT. And so this is the kind of thing that we're going to try and generalize. It's all about C numbers that you can imagine computing on some computer program to run CFTs. Okay? That's sort of the aim of the talk. Okay, if you take that metric and you go inside the horizon, and in fact you go towards r equals 0, then the metric can be approximated in this way. It looks like an anisotropic cosmology. And if you take the interesting bit of this anisotropic cosmology, it looks like a Lorentzian cone, a cone in space-time, where r is, of course, now time-like. And you see that the circles in the spatial direction are getting smaller. So the conserved angular momentum means that as you send particles in, their linear momentum at late time starts to grow as the size of the circle gets smaller. And so you have a kind of accelerator. And so even soft particles coming in at early times, thinking of r as time, early times eventually get accelerated, and you end up with hard collisions as you get towards the tip of the cone. And so rightfully, the tip of the cone is the singularity in general relativistic effective field theory. Just to say that it may be, and it's been argued by these guys, that in fact in weakly coupled string theory, that this actual mathematical singularity in effective field theory can be smoothed out by string theory within a string length of the n. Okay? So what's the goal of this talk? The goal is that you imagine being given a CFT computer. It will compute correlators if only you tell it exactly which correlator to compute. Okay? So you want to actually provide, our goal is to provide explicit correlators saying do this, but very explicitly, not implicitly or in principle. And these correlators have to sharply probe scattering inside the horizon in a way which is UV complete, non-perturbative, and diffeomorphism invariant. In fact, if you can do it on the CFT side, it probably is diffeomorphism invariant. The idea is not to replicate what you can do in gravitational effective field theory or what you can do in weakly coupled string theory, but in these regards, to improve upon that if somebody handed you the CFT computer. Okay? So that's the goal. Although these are the kinds of things that you might use to check that you're sane and you're getting the answers you think you're getting, at least in some region. Okay. So let me literally add more information to that first picture. Here is the sort of picture that I had drawn before, but now as part of a Penrose diagram for the extended black hole space-time. And so there is, of course, the inside of the future horizon, past horizon, the singularity drawn there. But then there's also this, going through this, you're getting to another asymptotically ADS region, and I'll just label it as left. So this thing, this extended space-time for the BTZ black hole, is dual to, again, 2 CFTs, left and right, in a state of thermofield entanglement. And I'll just use psi to denote that CFT thermofield state. And in the duality, it is the dual of the Hartle-Hawking state for gravity and matter in this space-time. Okay. So the kind of things you can compute once you have this level of expanding this picture is you end up computing, so a very typical thing is you'd end up computing left and right local correlators in the CFT, and they would correspond to sort of left and right boundary local correlators in the ADS spacetime or the gravitational spacetime. As a baby version of what we're actually intending to do, it's worth noting this simple equality, which is probably well known to many people and just a simple piece of algebra given the definition of this thermofield state, that you can take these local operators on the left and you can write them as a correlator where everybody is living here, except that these operators are no longer local. These tilde operators are non-local in the following sense, that they sort of have these fractional Boltzmann weights here, if you like. The way that these things give you the same answers, if you want to put words to it, is to sort of say that it's not that this operator is literally the same as this operator, but rather, because there's a particular entanglement in this theory, you're using sort of the non-local EPR twin of this operator and getting the same matrix elements. Okay? But that's a trick that we're going to try and generalize. So our goal is to imagine sending in to the future horizon, say, some particles, wave packets, that are going to scatter inside the horizon. They may scatter into small black holes, which then evaporate. They may scatter into Z bosons. They may scatter into Gauss particles. And then stuff comes out. Particles come out. And we'd like to capture this somehow on the CFT side with, as I said, non-perturbative level of precision and with UV completeness. Okay, so that's what the CFT is for. You can imagine sort of two strategies, for sort of two obvious strategies for trying to do this from the CFT side, and each has its issues. Okay? One is you can try to go back to the boundary. You can say, whatever came out here, let me try and measure it by calculating boundary correlators on the left and the right. And as you can see from the picture, that necessarily means going in some, at best, space-like sensitivity to whatever is happening inside. So that is certainly a direction, not this, but a related spirit of inquiry has certainly been followed in the past. And so there's some limited visibility of what's inside by taking that tack. Another tack is to say, well, the problem here is these particles that are produced in the out part of the scattering are heading off into the singularity. Let's head them off at the pass. Okay? So let's put down some bulk local operators to sort of catch them, and let's calculate those correlators. And let's hope that these bulk operators, these bulk local operators, can be somehow modeled in the CFT as some sort of non-local operator. Now, the perhaps deep problem is that there's no such thing in a diffeomorphism invariant theory like quantum gravity. There's no such thing as a local, truly local operator. It always means something in some sort of gauge fixed sense. But the other issue is really that you don't want to sort of have to work. So there are proposals to try and construct in some sort of effective field theory sense, or at least order by order in 1 over n. There is an attempt to sort of understand how to construct these bulk operators. But effectively what you're doing is solving the dynamics order by order in 1 over n to create the operators and then use them, but use them to solve to get the CFT to solve the dynamics. So there is some sense in which you sort of have to solve the dynamics as a precursor to even getting going. So again, this is not the tack that we're going to take. Instead, we're going to take this tack. So let me just walk you through it. This thing is where you should start looking. All it is, again, a thermofield expectation where you have, again, familiar left and right operators, but you also have a anti-time ordered string of non-local operators on the left and the right. I'm just calling them P and F for future reference. So you have this as a generalization. So it's clearly still some matrix element of the thermofield state. Now, these non-local operators are not the tilde operators I showed you before. They're a slight twist on them. They look very much like what I said before when I said how you could write a left operator as a right equivalent, where this is local, but this is non-local. Except that instead of using just the Hamiltonian, you're now using the angular momentum in the sigma direction, kind of a light cone Hamiltonian rather than a Hamiltonian. Okay. So that's the extra little twist. And then, even then, so that tells you what this means, but then there's a question of how to interpret this horrible thing. And you can just see that this thing is equal to this. I can simplify it, where I define these modifications of the thermofield state by acting with these non-local operators in this way. Okay. So instead of having the same state psi here and here, it's changed this to something I'll call psi past, and this is being perturbed to something I'll call psi future, and then it looks like, again, a left-right correlative. So these are the equivalent things. OK, so here's the central claim, that this modified, deformed thermofield expectation, it's no longer an expectation, this matrix element. Well, you can picture it. That's straightforward. We can picture it like this. We're putting in left and right disturbances on the boundaries, and we're sending in the disturbances. And these things can be visualized in the Penrose diagram as some sort of state, quantum gravity state, on some hypersurface that ends at on the boundary. So this thing, because it's just a calculation in the CFT thermofield state, it is certainly a thing you can compute in the CFT. I'm telling you exactly what it is. And the claim is that it sharply probes the inside. These matrix elements, right? There are many such matrix elements, because there are many ways I could have created psi f and psi p before, that they give a certain class, not all, but a class of sharp probes for this scattering that takes place here in brown inside the horizon. So these matrix elements, these states sort of act as the glove that catches whatever comes out of these scatterings. Okay. And the way they're doing it is because of the form of this thing, effectively just a generalization of this EPR-like story. That we're really, all we're doing is doing things on the left and the right with non-local operators, but we're getting the same matrix elements as if we had done this process. That's the claim. To prove the claim, we start with the simplification of the story, where we're not doing the black hole, but we're taking the size of the Schwarzschild. The Schwarzschild radius is taken to infinity. In fact, the way we've scaled coordinates, that means that the periodic direction, sigma, the angular direction, unravels and becomes infinite. Instead of being a circle, it's now a line. And that takes the so-called black hole, the black hole to the so-called black string solution. And the news there is simply that it is the Rindler view of ADS Poincare. Okay, so here is ADS, the Poincare patch of ADS, written in Poincare coordinates. And when you take RS to infinity, all we're getting is a Rindler view of ADS Poincare. So let me just talk you through ADS Poincare, at least the parts that are relevant for us. Here is ADS Poincare, the boundary here in black, parameterized by light cone coordinates, where time is, say, the average of the two, and the z coordinate going off in this direction. And these blue planes that come out like this, these are Rindler horizons. That is, they're horizons for some set of accelerated observers who don't go into the top and bottom wedges, but live their entire existence on the left and the right, the L and the R regions. Okay? And the coordinates that transform the black hole solution when you take RS to infinity, or just this, and these coordinates is just given here, and it's weird, but it's correct. Okay. At the quantum level, the holographic dual, from the Rindler point of view, the Rindler observer is only aware of the boundary that is outside the horizon, namely these two wedges here. And so it kind of breaks up the CFT that lives on the boundary into a sort of a left wedge and a right wedge, the so-called CFT left, CFT right. And the thermofield state is nothing but the standard Rindler way of writing the Minkowski, or in this case, Poincare vacuum. Okay? So that's how anything we've talked about, the thermofield state, becomes something more familiar, just the Rindler analysis of something with sort of Lorentz invariance. Okay, so here is the central technical result that's underlying the rest of the talk. It's just this, that this string that I told you about, this matrix element in the thermofield state, which involves these non-local operators with anti-time ordering, is equal to something very simple in this non-compact limit, where RS is equal to infinity, and we're really just a Rindler view of ADS Poincare. And here it is. It's just a completely standard time-ordered product with respect to Poincare time, not to this Rindler time. Poincare time, it's an absolutely standard thing like this. All these anti-time ordering things have disappeared. But the only thing that's happened is that these non-local operators have turned into local operators. But every time you've had any, I should have written the space-time argument here. The space-time argument here is being, the sign here is being flipped for x minus, okay? So whatever you can convert between Rindler coordinates and Minkowski coordinates, but whatever the Minkowski coordinates were up here, you flip the sign of x minus here, or if you want, x turns into t by going from here to here. So this is the translation, and it's true up to these phases. And these phases depend on conformal weights in this way. And the phases are very important for sort of getting all the right things that quantum mechanics requires, as well as relativistic causality requires. And I'll just illustrate that very briefly later. But this is the master formula. And because it's an ugly formula, well, first let me say, what's the vague intuition for this? The intuition is that in the tilde, you keep seeing these kind of factors. And roughly, they induce an analytic continuation on the space-time arguments of these operators. This thing would suggest this translation. And if you convert to Minkowski coordinates, it's exactly the thing I'm telling you. And this is very analogous to people may be familiar in the Thermofield context, where pairs of operators like this, which allow you to convert from left to right, induce this kind of analytic continuation. Okay. So here's the picture. The picture is that by putting these non-local operators in red and only calculating correlators outside the horizon, but involving these non-local operators, this translation of that master formula is basically telling you it's equal to correlators where everybody's in black. But now you have correlators that are inside the horizon as well as outside the horizon. Okay. So this ability to, in some sense, take non-local operators and get the correlations of local operators inside the horizon, inside the boundary, on the boundary inside the horizon, it can be done other ways. Okay. But this way is compatible with subsequent compactification to BTZ, and other ways involve symmetry operators, which are only symmetries of ADS Poincare, for example, this direction, and which are subsequently broken by compactification. Okay? So that's the general idea. The proof is diagrammatic. We just prove it in ADS using Witten diagrams. So I'm running short of time, so I'm not even going to walk you through this very simple case, which is a shame. But anyway, I think if I'm going to manage time, I'm going to not do it. But so the proof of that master formula is just studying the diagrams and being careful with your I epsilons and all of that. Okay. So we want to go back to the compact case. It's not all about Rindler CFT. It's about BTZ CFT. But the Rindler case, this is the answer to how we probe scattering inside the horizon. Ultimately, these non-local operators are allowing you to send in particles. They scatter inside the horizon between these two blue planes. And then whatever comes out, it's caught. It's measured by these things which are time-like separated from the scattering, or the scattering region, namely the boundary region inside the horizon. And we can get those boundary correlators inside the horizon by using non-local operators on the outside. Okay, so we have the exact answer to how to do that. That's the non-compact case. Now, what's the whole problem with the compact case? Okay, well, the main thing is that if you want to go back to the compact case, you have to recognize that BTZ is a quotient of ADS3. Roughly, you're trying to take the non-compact sigma and make it periodic in this way. But if you go to Poincare coordinates, that means making it periodic in this way by discrete scale transformations by e to the rs. Lambda just means e to the rs. So if you take a radial line like this, it really corresponds to moving in the sigma direction. And if it's periodic, then this becomes a periodic circle. Okay? And now you'll see the problem, or the issue, that this thing is a space-like direction, and so it'll turn into a space-like circle. That's what we were hoping for. But these lines that lie on these light cones are obviously, they're light-like lines, and yet they are still periodic, and so they turn into light-like circles, which means that the circumference of the circle is 0. And that perfectly matches what I told you about the singularity. The singularity is the place at which the sigma direction circle goes to 0 circumference. So that's this way of picturing the singularity. And then inside, even beyond that, in this picture, it's not caught by the Poincare, by the Penrose diagram, are these time-like sigma directions which turn into time-like circles, presumably very unphysical. Okay? So the problem we're facing, well, first let me just say one thing. We're going to use Feynman diagrams. So other than talking about colliders and cosmic accelerators, we'd like to see in Feynman diagrams why things go bad at the singularity. And it works by just taking the BTZ propagator. You throw something in, and then you see what the reaction is close to the singularity. That's called the propagator. And you calculate it by method of images from the ADS propagator. And here are the images, right? These lambda the n's, three scalings. For generic points, you find there's a lambda to the n up top and a lambda to the 2n on the bottom. And so the argument always gets small as n gets large. And when it gets small and you use the asymptotics of Bessel functions inside this G, you find that the images become very small very quickly generically. However, if you live right at the singularity, that light cone, if you live right there, then the lambda to the 2n bits cancel, and you get lambda to the n over lambda to the n, which is something that's independent of n for large n, and you're summing it an infinite number of times, and you get infinity. And that's the singularity in diagrams, or that's at least the root of all evil of these diagrams. So the problem that we face is simply that we are trying to emulate the non-compact case, where the moral is scatter inside the horizon and then try to catch things using local operators on the boundary region inside the singularity now, okay, inside that cone. And now that means it's inside the singularity. So somehow it looks like our plan is, however much we dress it up with non-local operators, the plan is that you have to catch the scattering, right? You're trying to measure the scattering process and features of the scattering by scattering through the singularity, and surely that's crazy, okay? So let me just say why it's not crazy. Okay? First, let's just get our expectations set up using the non-local way of thinking about it, the Rindler way of thinking about it, rather than this way. So here's a comparison of these two ways in the non-compact case, where everything is above board and there's nothing up my sleeves. Okay? So this is the way that you sort of calculate. So this Penrose diagram is drawing it as if it's emulating what we do in the compact case, except the Penrose diagram, just like in the compact case, we usually don't draw this region of time-like circles. So everything inside these cones is thrown away. I'm just going to throw away those regions for comparison and draw a Penrose diagram here. But now we have to recognize that these are those cones. And there's nothing singular about it in the non-compact case. Okay? Nevertheless, this funny string of non-local operators and local operators is given by this sort of folded time evolution. The folds are coming from the anti-time ordering. Okay? So your anti-time order, then your time order, then your anti-time order. And so that sort of looks like this. And it, basically, all these anti-time ordered folds are setting up these states, these perturbed states, psi f, psi p. Okay? In the other way of thinking about it, the equivalent way of thinking about it, where you just say, no, I'm just scattering to a local operator that's beyond those cones. Okay? In that language, you can think of this state as just being sort of backing down whatever this operator did. Okay? So you take the Thermofield state, this thing disturbs it in some way, and you back it down here. So these are just the equalities that those formulas were meant to give you. But notice in this language, in some sense, the time evolution never gets close to this, this line, this cone. Okay? So that when you compare now the non-compact or Rindler case with the singular case, with the black hole, which actually has a singularity here, in both cases, this folded evolution, or if you want, let's start here. This is our proposal. The folded evolution is always happening where the circle, the sigma circle, is large. And so you might expect that it's approximately the same as when it's infinite, okay? Whether our universe is 10 billion light years and it's a circle, or whether it's just infinite in the spatial sense, doesn't make a whole bunch of difference to us. That's very much the expectation that you would have here. Okay? You're really secretly not going near the singularity. And indeed, the subtlety here is there are these tilde non-local operators. Maybe they sense the size of the universe. They're very similar to Boltzmann weights. When you do this, it's well known that you're just insensitive to the size of the universe when you just go in this region. Okay? That's our expectation, and then you can technically check it. Okay? So you take diagrams that seem to go into the boundary region inside the singularity, right? There's this cone here. This is the region, the zone where you're inside the singularity. And you use method of images, so it's really this plus all the images. And the main thing is to sort of come up with an efficient way of showing that, in fact, everything we just claimed in those previous pictures is true, can be done efficiently. You can do it just by being careful about I epsilons, or you can be efficient by doing the following move, which is that when you have interactions in Witten diagrams, they are sitting at some z, and the z integral, you can contour rotate. Okay? You can check that you can rotate z to e to the I theta z for some large enough theta, and that you don't go into any singularities or branch cuts or anything of the ADS propagator. So this is something that you can do. Thanks. This is something you can do. And when you do it, you find that, say, for some intermediate phase like I, you find that, in fact, you never get cancellations, and you're always having propagators which are small in this, where the image terms are small in this sense. Okay. Note, this is not saying something crazy. If you actually have a diagram which ends on the singularity or ends close to the singularity, all hell breaks loose. But when you're really doing this protected set of correlators, which go from boundary to boundary, then you actually have this, nice feature. Ultimately, it's due to cancellations inside and outside the singularity when you integrate Feynman vertices inside and outside the singularity. So I've run out of time. Let me say this quickly. Basically, what this shows, is that these non-local correlators in CFT squared living on a circle, CFT on a circle, there's a substantial number of them that are actually capturing in the same way that you do in Rindler space. In fact, they're approximately equal to the Rindler scattering amplitude. They're capturing scattering inside the horizon. And roughly the sharpness, when I say the word sharp, is roughly the sharpness that one has when you don't compactify for correlators in the Poincare patch of ADS. Okay? So in some sense, you can get more sharpness from local correlators in the global ADS than the Poincare patch, but at least this is the standard we play by. Most of what I just talked about was sort of erring on the side of theoretical control, finding correlators where we could actually see that they are probing the interior, and yet we can calculate something without even an effective field theory to check. Ultimately, you want to go in this direction, and I'll just conclude and tell you, so I'll talk through that. Here's sort of where we end up. These local, this is just for calibration. In standard ADS CFT, local correlators in ADS or CFT correlators give you a non-perturbative diffeomorphism invariant UV complete S matrix, or at least a generalization of S matrix for ADS quantum gravity. That kind of an S matrix seems absolutely impossible for cosmological spacetime because stuff goes into the singularity and then there's no S matrix sense in which you can capture it. However, that's exactly what we're claiming is happening here, where we can, first of all, check these correlators that go in the singularity and even beyond, and at least a class of them are under control. And we can also render them in this sort of Thermofield language as non-local operators where nothing ever goes near the singularity as well, but it does probe the interior of the horizon.